right, on we go. So for this problem, I want to study this particular limit. And I want you to ask yourself for just a moment, what would you do if I asked you to take the derivative of this function? Pause the video, think about what you would do to take the derivative of this function. Well, hopefully you notice that there's a variable in the base and there's a variable in the exponent, and hopefully that made you remember the moment in class a little while ago where we learned that we could actually throw a natural log into this problem, change the problem, and then get the derivative we wanted back. So our dream came true in that situation. But surely you'd say, surely it can't happen again. Well, actually it can. So let me show you why we can actually take the natural log of this guy and recover this limit. Once I take the natural log, it's a different limit, but I'm going to be able to recover this limit. And here's a little detail of why. I'll just make this a note. And so the note is, let's assume that my function f of x is strictly bigger than 0. Okay? So then I claim that f of x is equal to e to the natural log of f of x. Why is that true? Well, because ln of x and e to the x are inverse to each other, and since f of x is bigger than 0, then f of x is in the domain of the natural log, and so this composition works. You can look back in your notes. This is just basic properties that we talked about with the exponential function. So the point is, if you want to study the behavior of f at a point, if you want to take its limit at a certain point, well, natural log is continuous and on its domain. E to the x is continuous on its domain. And so here's the deal. Whatever f of x does, it's the same as e to the natural log of f of x. So if you know what ln of f of x does, then f of x is just e to the ln of f of x. So let's see this via example. Here we go. So what I'm going to do is I'm going to compute a different limit. Okay, so I'm going to look at the limit as x goes to 0 from the right of the natural log of x to the x. I'm not saying equals. If I said equals, that would not be true. They're not the same, but that's what I'm going to study. Of course, I'm immediately going to simplify this and write this as x ln of x. Then I'm going to say, wait a minute, gee, this feels really familiar. I feel like I've seen this problem before, and I'm going to scroll up in my notes. Hopefully I don't go too fast and make you seasick. Oh my goodness, problem 4, we did this very problem. So we saw that x ln of x as x goes to 0 goes to 0. So we can scroll down now, and we say, well, we know that this one is equal to 0, and let's say here's C number 4. All right. So since we know that the natural log of our function goes to 0, we can say thus the limit that we want, the limit as x goes to 0 from the right of x to the x, the original function, is not 0, it's e to the 0, which we should write as 1. So that's how you can actually use natural log to make life easier for you when it comes to taking limits. Okay, so next problem. I've got the limit as x goes to 0 from the right of 1 plus sine of 4x to the cotangent of x. And I'm going to notice right away that the inside of this guy has a variable, and it's also raised to a power. There's a variable in the base and the exponent. So that suggests somehow that I'm going to want to take the natural log of this. Let's check the form before we do that and make sure that it really is a determinant. As x goes to 0, the inside, the base, is going to 1. And the exponent, as x goes to 0 from the right, cotangent goes to infinity, so this is indeed indeterminate. So I want to look at not, I'm not going to say equals, but I'm going to look at a different problem. I'm going to take the natural log of this guy, and when I do that, the natural log of the whole thing, I can pull the cotangent down, and so I'm going to write this as cotangent of x times natural log of 1 plus the sine of 4x. I'm going to check the form now. Notice that cotangent of x is still firing off to infinity as x goes to 0 from the right. But now on this side, as x goes to 0, the inside goes to 1, ln of 1 is 0. So the form is now infinity times 0, it's still indeterminate. I'm wanting to use L'Hopital's rule somehow, but I don't have a fraction. But I'm inspired to try to pull the cotangent of x downstairs. So I can write this as this guy over 1 over the cotangent, but 1 over the cotangent of x is just tangent of x. So this is equal to the limit as x goes to 0 from the right of the natural log of 1 plus the sine of 4x over the tangent of x. Check the form. We want to use L'Hopital's rule. I want to make sure the form is correct. We've already seen the top is going to 0, and as x goes to 0, tangent goes to 0. So we've got the right form. We can finally use L'Hopital's rule. So this is the limit as x goes to 0 from the right, the derivative of the top. Let's pause and think about that. Pause the video, think about how you take the derivative of the top. Hopefully you know the rule. When I have a derivative of the natural log of something, it's the derivative of the inside over the inside. So this is just 4 cosine of 4x over 1 plus the sine of 4x. Okay, then I do L'Hopital's rule, take the derivative of tangent now, and I get a secant squared x downstairs. And now I want to see what happens as x goes to 0. Do I get a constant? Do I blow up to infinity? Do I get indeterminate form? Let's just see what happens. So as x goes to 0, the top is going to 4 times cosine of 0 is 1. The top's going to 4. The middle fraction, sine goes to 0, so this is going to just 1. So 4 over 1. Secant of 0 is 1 as well. So actually we've got it. This is exactly 4 over 1 over 1, which is just 4. I'm not done. That's not the answer. We took a natural log, so that's a different problem. The problem that I want is going to be e to the 4th. I don't really want to rewrite it, so I'm going to say something like this. I'm going to say thus the original limit is e to the 4th. And it's important that we point out the original one. That's the one we wanted to solve, not this modified version.